A tennis ball with a mass of 60 grams is served using a variable force described in the graph below. Find the final speed of the ball assuming the ball was at rest when served. Okay, so we're trying to find this final speed, and we are given some information. So first of all, mass, we're given mass. This time we're actually going to use the mass, unlike last time. We converted it last time even though we didn't use it. Whatever, who cares? Let's see, so that's that. 60 grams, 2 kilograms. Oh, and we're doing that because standard units. Final speed, so we're trying to find the final velocity. Over here, like, we're not really using direction, so like, if you want a velocity and speed, we're just gonna say they're the same thing. And we don't know that, we're trying to find that. So, that's our very important very important variable, VIV. So, and we're assuming it is at rest when served. And so we actually have its starting momentum, but it doesn't really matter. Starting momentum would be 0. Well, it does, from a theoretical standpoint, it does matter, but, it's kind of obvious. Okay, because m times v is, in this case, it's 0.06 times 0, which, believe it or not, is 0. So find the final speed. Okay, first of all, what we're going to do here is we're going to find the impulse, the change in velocity. And since the initial velocity is 0, or we're going to find the final we're going to find the impulse, which is the change in momentum. And since the initial momentum is 0, the change in momentum is just going to be the final momentum, because change in anything equals, okay, let's say change of x. The change of a variable is the final amount for the variable minus the initial amount. So you have 1 point, and then it changes, and then you have your second point. And the first point is 0 for the momentum. So we're looking for final speed or velocity, And how do we do that? Well, first of all, pretty important. I'm kind of backtracking here. I know I already said this, or I implied it at least. But momentum is mass times the velocity. It's a really simple formula, right? So the final momentum, okay, another thing, we're going to say change of p equals, this isn't really something you need to write because it's just really basic, and I don't think people would, or any teacher or grader would take points off from you for not writing this, but I'm going to write it anyways because we're going to use it, and it's going to help explain something that's sort of obvious, but still useful to know. Then we're going to finally write J, impulse, is the change in P. It's the change in momentum. No jokes there. And it's equal to force times time. Again, I showed why this is the case in the last video. Change of P would be change in mass times velocity, and since the mass is constant, it would just be mass times change in velocity, and change in velocity is acceleration times time, because acceleration is change in velocity over time, and when you multiply change in velocity over time times time, you just get change in velocity. Okay, so that's just a really summarized reason for why. Let's find the impulse rate. So we already have, also for our data, because we are using force and time, we're going to write that down for our data. So first of all, 0.045 seconds, that's our time. Right. Second of all, our force. Okay, so we're given a final force here, or not a final force, we're given a maximum force here. But this isn't the force we're using. Why? Because if you said that okay, let's just imagine a system where someone applies 5 newtons of force over a time span of 2 seconds. Uh, and I'm sorry for my, I would say, you know what? Okay, I'll say it again. I'm sorry for my handwriting, but first of all, I'm not getting paid to do this, and second of all, like, I'm not a professional computer graphics artist, so I don't have a professional graphics artist pad. Okay, so if you graphed this 5 newtons at, over 2 seconds, and let's say your y-axis would be force, and your x-axis would be time, you would see a constant 5 newtons over the 2 seconds. It would just be a straight line, right? This would be 5, and this would be 2. So 5 this line is just to show, okay, let's see, like that. Right, so you'd have 5 newtons, 2 seconds. Right. Now, if he had an average of 5 newtons over 2 seconds, it could be really anything as long as the average was 5 newtons. So it could be, let's say he had 10 newtons at 1 second, or for, yeah, exactly, let's say he applied a force of 10 newtons for exactly 1 second, and then it dropped down all the way to 0 newtons for the next second. You could average the two and say that he averaged 5 newtons over the 2 seconds, right? A triangle has an average right in them. Let's say this is at a point Y. No, let's say this is a point A. So the average of the sort of Y amount for a triangle is at the point 1/2 of A. Basically, a triangle's linear, so it's going to have a linear relationship. The average of these two x points, like point 1 and point 2, would be in between them. In the same way, we have our graph here. Oh, I think I might have erased something important, but who cares? So just, I know that was a long explanation, but basically it's just saying the average is in the middle. Whoa, rocket science. So we're just finding the average here. Let's see. And our average would be 375 divided by 2, which is 187.5. Actually, I won't even write it here. I'll write it. Okay, so 187.5 newtons. Force newtons. Right, so now let's find our change in momentum. What is 187.5 times 0.05? Good question, me. The answer is, give me 1 second, it's 8.4375. Okay, so what does that exactly mean? That means our momentum went from 0 to this point, 8.4375, which means this is equal, since this is our change in momentum, this would be PF. I could write PI, it's PF minus PI, but PI is 0, so let's just skip that step. I'm lazy. Okay, so that's our PF. Actually, let me just go up for a bit here. Okay, how's that? Okay, so what is PF? Well, besides 8, and the units here again are newtons times seconds. But this is, we're in the calculator, and this would be step 3. All of this is step 3. Okay, so our, what is this? What is the final momentum? Well, the final momentum is, well, first of all, momentum in general is mass times velocity, right? So this final momentum is the final mass times the final velocity, right? But the mass is constant, so it doesn't matter at what point, it's just at what point you're at in this whole system, it's the same amount. So the final momentum equals mass times final velocity. And now let's just have some substitutions here. 8.4375 equals 0.06 times final velocity. And again, since we're in standard units, it all checks out. As in, this is newtons times seconds, this is kilograms, and this is meters per second, but newtons equals it's kilograms times meters per second squared, I believe, because acceleration is in meters per second squared. So yeah, it all makes sense. So now, doing some basic math, we all know that 8.4375 divided by 0.06 equals 140.65. Actually, again, we're going to round this to 141 because that is the because 3 sig figs, and it's measured in meters per second because it's velocity, and that's our final answer. Now, step 5. This is interesting because if we do a quick Google search here, as my friend Riker pointed out, the speed of sound is, okay, you can't quite see it, but it is 340.29 meters per second. Or it says here it's variable, but over here 343.2. Okay. This is going at over a third of the speed of sound, but we're not going to worry about that because it just checks out with our math. So for step 5, you could say that the change in momentum is high and the mass is low, so the final velocity is going to be high, or something like that. But yeah, so it all checks out, even though it's really sketchy. So yeah, thank you.